filtering, Kalman filtering, try to extend it to the nonlinear case, and then talk a little bit about SLAM. We have enough time. Uh, sorry. Um, okay, great. So on logistics, we're going to have this seated paper discussion on Friday. So 3 teams should be assigned. If you're assigned, meet up with your team members, come up with an idea. Unclear, stop by after class. We'll talk about the details. There are some issues with the stolen battery, or not stolen, missing battery. But please be careful about, not accidentally taking things, and yeah, those are each expensive, so be careful with it. I guess one more piece of logistics is I have to be in San Francisco on next Wednesday. Um, gotta get that money, man. I don't know. But um, I'm I'm happy to remote lecture. We can do guest lecture. We can reschedule to Tuesday. What would we prefer? Like someone else will, like I'll have my postdoc or someone come lecture, or I'll have, yeah, someone else lecture. Okay, but it's not a guest lecture like a normal guest lecture. It's like a guest lecture on the material. Okay, I can find out. Okay, so maybe guest lecture first, then remote, then reschedule. Is that right?
Maybe guest lecture and mostly.
Remote same. Okay. Was
Reschedule like that.
yeah, I would love reschedule. Was the remote lecture just like hard to parse last time? Was it doable?
Same as.
It was okay. So I'll try to find you a guest lecturer who's engaging. If not, we'll just do remote. I'm sorry. I just like travel they just booked in the middle of the week. So I'll have to get money for this university. They're cutting all our funding. Okay, good. All right. Any other logistics questions that we need to discuss? All righty. So let's quickly get through our little quiz. The question is, the dynamic step of a Kalman filter always shrinks uncertainty, always grows uncertainty, may grow or shrink uncertainty. Uncertainty here is like the variance of your belief. Yeah, possible. Make of it what you want. I didn't think that. I didn't think that deep about it. Cool. All right, let's keep moving. So the answer here is that depending on your your choice of the A variable, your uncertainty can shrink or grow, right? So if your A, for instance, is a 0 matrix, your thing is always going to go to 0, and your uncertainty may reduce, right? And so it's not always true, but it grows. Okay. How do we feel about the Kalman filter? Should we recap it? Do we feel pretty comfortable? What's the deal? How do we feel about it? Maybe thumbs up for comfortable. Thumbs sideways for okay-ish, right? And maybe thumbs down for recap all the way. Okay, thumbs sideways. Okay, let's recap it somewhat. I'll skip over the easier parts and go over the details of the harder ones. Okay, so remember, Kalman filter is a Bayesian filter where your motion model and your dynamics model are linear Gaussian, right? And so we're going to deal with Gaussians, and so we're going to use these two identities. The first identity, which I'm calling forward propagation, is saying that if you have x as a Gaussian and you have a linear function y with some additional noise, the noise is also Gaussian, then you can say that y is distributed according to a mu plus b as your mean and a sigma a transpose plus q as your variance, right? So this is just a linear shift on the mean because you have a linear shift of y with respect to x, and your variance, you can think of this as a quadratic scaling with respect to a, plus the extra q that is coming from this extra noise. And so when I say the uncertainty doesn't always grow, it's like if these a's are like shrinking, then your uncertainty may shrink, right? They have eigenvalues less than 1. Okay, so you can kind of think of this as saying, like you had your uncertainty here, your A is going to shift it here, and then there's going to be some growing of the uncertainty, right? So that's kind of our forward propagation step. And then we have the conditioning step, which is a little more confusing. But we've said that, okay, let's say you have x and y. Y is a linear function of x. And you were saying that if I had more information about what y was, can I refine my distribution of x? And we're saying that, yes, you can refine it by saying, you can refine it by saying that your mean is adjusted by interpolating between your mean and something that is the difference between what you got and what you expected to get, right? So this is what you actually saw. This is what you expected to get if all of the probability mass was at the mean, right? And you're saying, look at the difference between that, and that tells you how much to adjust your mean. And this term here is saying you can shrink your uncertainty according to like this K factor is like how much you should trust your sensors. And so it's saying like, depending on how much you trust your sensors, you can shrink your uncertainty. And so we're going to use this for our prediction step. We're going to use this for our measurement step, right? Okay, so that's just a quick recap. So once a Gaussian, always a Gaussian, as long as you're linear, right? And so our Kalman filter we're going to do a discrete Kalman filter. The discrete Kalman filter is represented like this. It's saying that xt is axt minus 1 plus but plus epsilon t, where epsilon t is coming from a Gaussian with mean 0, variance q, right? So it's linear and it's Gaussian. Your measurement model is also linear and Gaussian. It doesn't have any actions in there. It's just based on your current state xt, and this coefficient c, right? So it's saying that like your Kalman filter is defined by a, b, q, c, and r. Yeah. So that's our system. Okay, so let's try to work through what Bayesian filtering looks like. So Bayesian filtering, if you remember, had 2 steps. It has a dynamics update, which tries to go from belief to belief bar, has a measurement update that tries to go from belief bar to the next belief. Right? And so the first step is we're going to try and compute this guy. The second step is we're going to try and compute this guy. Yes? So we're going to try and instantiate the dynamics update and try and instantiate the measurement update. Okay. So let's skip through this. We're going to initialize our Kalman filter with some, some mu naught, some sigma naught. Let's say we like chose this by hand, right? And what we're going to use as our notation, if you remember, is mu t 0 to t, sigma t 0 to t, saying what is the mean at time step t with evidence 0 to t? What is the mean at time step, or what is the variance at time step t with evidence 0 to t, right? And so we're going to start with mu naught, sigma naught, and then you're going to use our updates to get mu1, sigma 1, mu2, sigma 2, and so on, right? And so you're going to have like a simple update that goes from mu naught, or simple-ish update. It's going to go from mu naught, sigma naught to mu1, sigma 1 to mu2, sigma 2, and so on, right? And so the Kalman filter is really about instantiating what this update is, right? So how do I express mu1, sigma 1 in terms of mu0, sigma 0, and so on? Okay. The setup makes sense? Any questions? Okay. So the first step we're going to do is the easy one, which is the prediction step, right? So the prediction step says we're gonna, there's a lot of stuff on the slide at once, but let's kind of look at it one by one. So this guy is just your system, right? So it's saying like we want to go from belief at time xt to belief bar at time step xt plus 1, which means I just want to incorporate the latest action, right? Not the latest measurement, just the latest action. And so what I'm going to try and do is try and say that like I'm trying to do pattern matching, right? So I have this identity which says that if I have X, which is Gaussian, Y, which is linear, then I can express the distribution of Y in terms of the distribution of X, right? And so someone remind me if I'm trying to do the dynamic step, what is X, what is Y, and like how do I do pattern matching here? So I want to be able to use this identity to go from belief to belief. At time step t is going to be a Gaussian. Let's say it's Gaussian, mu t 0 to t, sigma t 0 to t. And I want to express belief bar, which is going to be a Gaussian of mu t plus 1, 0 to t, sigma t plus 1, 0 to t. Okay. And I want to express that in terms of the previous belief and A and B, or A and B and Q. Okay. So I want to express this next time steps belief in terms of previous time step belief and A, B, U, and Q. Okay. So let me pattern match. How do we do this? Yeah. It is. That's why it's a recap. So quickly, so since we know it, quickly, so that help me pattern match it.
I guess A represents your second.
So A represents A, B represents BU, right? Right. So if you think about the next belief, what would it be? Like A, that's right. That's perfect. Right. So that's the mean. Right. So that is what the mean mu t plus 1, 0 to t is going to be. Right. And then similarly, sigma t plus 1, 0 to t is going to be
A sigma.
yeah. So you're going to directly use this identity. Think of X as your current belief. Think of Y as your next belief. A is A, B here is BU, Q is Q, right? Just pattern match to directly use this identity. And so intuitively, it's saying you're gonna move at the next step. You're gonna move your mean by A mu plus B, right? So you're gonna linearly shift your mean, and then you're gonna expand your variance by scaling it quadratically with A, which is your dynamics, and then add extra noise from your uncertainty. Yeah,
So this A and B is your like dynamics matrix, right?
that's right.
And then when you say like Q and QT plus one, like how do you decide how much noise you add? Is it just set or is it change?
You often just set it as part of your process. So it's like, it kind of captures how uncertain you think your model is, right? So you set it by hand often, or fit it according to some param. Like you often fit it as a parameter of your model. Okay. Does the dynamic step make sense? So remember, it's like intuitively, I have the intuition here. Good. So intuitively, you can kind of think of it as like blue was your previous belief. Your next belief is going to be shifted. Right? So think of it as you took the mean, you shifted the mean by A mu plus B, and then you expanded the variance, in most cases, by scaling quadratically with A, and then adding some extra noise because of Q. Right? So you shift it, and it's a little wider. So that's all the dynamic step is doing. Okay, good. All right, so the dynamic step was the one that we went through in more detail. The measurement step is more confusing, right? So let's think through this. The measurement step is saying zt plus 1 is cxt plus 1 plus delta. And belief bar is basically everything except for the last measurement, and belief is including the last measurement, right? So you're trying to incorporate the last measurement. You're trying to do Bayes rule on it. Right? So you're trying to do conditioning, right? So you can kind of do pattern matching. So remember that belief bar is at xt plus 1 is the likelihood of xt plus 1 given u0 to t plus 1, z0 to t. Belief is the likelihood of xt plus 1 given u0 to t plus 1 and z0 to t plus 1. Right, so like the difference is this versus this, right? Just one extra conditioning variable. Right, so if you think about this thing, it's just this thing, but more conditioning, right? So the extra conditioning is you're conditioning additionally on zt plus 1. Right, so the difference between this guy and that guy is that thing just has an extra conditioning on zt plus 1, so it gets more evidence. Right, so you're incorporating, if you remember how we did a particle filter, you're incorporating the latest measurement. That's it. Right, and so we're going to try and recast it in terms of this identity, right? And so this identity said that if you had, you know, a random variable, you had another one that depends on it, you found out the value of the thing that depends on it, and you do conditioning, you can refine the likelihood of x, right? So in this case, we have some belief over xt plus 1. zt plus 1 depends on xt plus 1. We got the value of zt plus 1, that's our measurement, so we can refine the belief over xt plus 1, right? It's exactly the same problem. So we're going to try and do pretty much the same pattern matching exercise we did earlier, right? And so our pattern matching exercise is going to be that x here is kind of your belief bar, y here is kind of your measurement, ignore that b, and r here is the same as like r here, right? And so we're going to basically directly use this identity just with like change of variables, right? I haven't told you what k is. We'll get into what k is in a second. Okay, but if we just kind of use this identity, we just pattern match x to belief bar, y to the measurement, and what we care about is x given y equal to y naught, which is basically belief at xt plus 1, including the like latest measurement, right? So it includes u0 to t plus 1 and z0 to t plus 1. So we're looking for this guy, which is the same as this. We're just going to pattern match it with this thing. Okay. So just look at that guy, look at that guy, pattern match, directly use your identity. So let's walk through what it looks like and then we'll intuit it a little more. So your previous belief after the dynamic step, let's say it was mu t plus 1, 0 to t, sigma t plus 1, 0 to t, right? Now, your updated belief is going to look something like this, right? And so we're going to get this directly from pattern matching. So if you look at this guy, right, it's basically exactly the same as this guy. Yeah. So we're saying that like the mean is the previous mean plus some correction term, which is a linear scaling of the difference between the measurement you got and the measurement you expected to get, right? And the variance is the previous variance minus like some scaling term, which depends on this k variable, and k is telling you how much you should trust your sensor, right? And we'll talk about that in a second. Right? So this is how much you should trust your sensor. So you can kind of think of it as this one is doing a mean adjustment according to how much the measurement differed from what you expected, weighted by how much you should trust your sensor. And your variance is reducing according to how much you should trust your sensor. So this variable k is called the Kalman gain. And it's kind of like a measure of how much you trust your sensor. Okay. And so the Kalman gain is often written like this. So it's basically sigma C transpose, sigma C transpose plus R, something like this. This is the Kalman gain. Okay. So we'll think about this intuitively in a second and work through it. But moving my scribbles, you're just saying adjust the mean by the difference between what you got, what you expected to get, weighted by how much you trust your measurements, and adjust your variance according to how much you trust your measurements, right? So you can kind of think of k as something that sits between 0 and 1. If k is 0, you don't adjust your mean, you don't adjust your variance, right? So if k is 0, this is 0, this is 0, everything remains the same, right? So think of k equal to 0 as like the measurements mean nothing, right? And think of k equal to 1 as the measurements is everything. Right? So if k is equal to 1, then you shrink your variance to 0 and you like completely adjust your mean to the measurement, right? So it's like that's k is equal to 1 means your sensor is essentially noiseless, right? And k is equal to 0 means your sensor is like very, very noisy. Okay. Does that intuitively make sense? Go ahead.
I guess. So can your uncertainty like increase after the measurement step without because like the k is always between 0 and I guess isn't C also like always positive? And C like
Yeah, so your uncertainty will not increase, right? Because yeah, this thing will always be smaller than what. Yeah, good question. So because like this term over here is going to look like C epsilon C transpose by C epsilon C transpose plus R. That's always going to be smaller than 1.
And also like I guess it's a good way of thinking about like C times mean, just like thinking about like what measurement you would have gotten if like
Yeah. So one way of thinking about it is there's like two different spaces. One is the state space and one is the measurement space. And C is just what transforms you from the state space to the measurement space. And K kind of transforms you back.
So like, I guess if your state space was like position and velocity,
Right.
measuring.
Right. Whereas your sensor space is like LiDAR beams. It like translates you between those spaces. But your state space could also be, for instance, LiDAR beams, and then they're in the same space. But in general, like C is translating you between state space and measurement. They need not be the same. Okay. So this thing is called your Kalman gain. You can kind of think of it as a measure of how much you trust your sensor. So let's think about this intuitively. So let's think about this update, right? And let's think of the state space and the observation space as kind of the same for now. So let's make C equal to identity, just to make our intuition simpler. Okay, so now C is equal to identity, which means our Kalman gain, you can kind of write it as sigma divided by sigma plus R, right? C is identity. So this thing used to be sigma C transpose by C sigma C transpose plus R. These guys are all identity, right? So it's sigma by sigma plus R. So let's think about the first case. Where do I have this? I think it's on my next slide. Okay, so let's think about C equal to identity. And K now reduces to sigma by sigma plus R, right? So let's think about a situation where R is really, really big. Okay, so if R is really, really big, what happens? What is K equal to? 0, right? So if R is really, really big, that means K goes to 0, right? And if K goes to 0, that means this update doesn't change the mean. This update doesn't change the variance, right? So like that means you cannot trust your sensor. So you can kind of think of it as your sensor is giving you Z sample from CX plus delta. Delta is sample from a Gaussian with 0 and R, right? So if this R is huge, that means your sensor is giving you like all sorts of noise. And if your sensor is giving you all sorts of noise, that means your K goes to 0, which means your measurement update doesn't do anything, doesn't change anything. Does that make sense? Okay, so think of Kalman gain as just like sigma by sigma plus R. And as R goes really large, this becomes close to 0. And the flip side is, let's say, R is 0, right? Like there's no noise in your sensor. So if R is 0, then your K becomes equal to 1, right? And if K becomes equal to 1, then your variance goes to 0, right? So you like instantly collapse, right? So like you can kind of think of it as that means your sensor is perfectly accurate. So I don't need to have a belief. I just like exactly know where I am. Right? And so this kind of passes our sanity check. Okay. So the general Kalman filter algorithm, everyone kind of this measurement step makes sense. So let's kind of make sure we fully understand it. You adjust the mean according to how much you trust your sensor and the difference between what you got and what you expected to get. You shrink your variance weighted by how much you trust your sensor. Right? So the overall Kalman filter algorithm is very simple. Once you get through these things, it's you have a dynamic step. The dynamic step just says, I'm going to update my my mean in closed form, which is a mu plus b. Your previous mean was mu. Your new mean is a mu plus b. Your previous variance was sigma. Your new variance is a sigma a transpose plus q. Scaled up variance, translated mean. That's it. The next thing is you're going to get a measurement, right? Your measurement is going to adjust your mean, adjust your variance, as we just said, adjust the mean according to the difference between what you got, what you expected to get, and shrink your variance according to how much you trust your sensor, right? And this gives you, so this was like going from belief to belief bar. This goes from belief bar to belief. And then you like plug these new values of the mean into like the next update. You just repeat this recursively, right? And so the nice part about it is you don't have to do any particle filtering, number of particles, seed them, resampling. It's all just in closed form. Like you just have to do matrix multiply, right? And so it's super efficient and like simple once you work through the math. Okay, questions? Does it generally parse as an algorithm? So why is this useful? This is a weird, creepy robot baby I found.
Estimator is
and,
validated with accumulated flight
It's
scenarios
an example of
in
like a robot
the plot on the bottom left show
that
individual
you're trying to
test
track.
intensities estimates
Right, so it's a
by two
system you can
estimators'
kind of think of these
variations.
as like
The first is the
tracking
estimator we
different
propose,
anchor
and
components
the
to
other
various
is a
components.
variation
You
of
can
it
see that the
that
measurements
discards
are kind of
its
noisy,
dynamics
right? So
and
the
depends
measurements here,
only
I
on
think,
the
are
robot's centroidal momentum dynamics.
the measurements are kind of
We
noisy.
can see that both estimators
But like
converge
the
to the
green line
simulated
is
thrust
filtering them out.
intensities.
So sometimes you have spikes
In the
and so
bottom
on.
right, we see the
And your
robot's
Kalman
centroidal
filter will kind of
momentum for
smooth through
linear and
those things,
angular components,
right?
compared
And
with the
so
estimated
in
values
general,
against
if
the
you ever
measured
have a
values.
situation where like an example that some of you might see is like motion capture, like you have a robot in motion capture, and like the state is jumping all over the place. And if you like stick it through a Kalman filter, it just like kind of serves like a smoother, right? And it like will smooth your state, so it'll like prevent it from jumping way all over the place. Right? So if you get like, for instance, a measurement that's like way off, it doesn't just directly jump to that measurement, which is what dead reckoning would do, but it like incorporates it with belief. I guess a rolling average doesn't take into account how confident you are in your measurement. And so a rolling average would always treat everything equally. And this kind of like gives you more nuance as to like which places you're confident in, which places you're not, which dimensions you're confident in versus not. So you can like put a little more information as opposed, you can kind of derive a rolling average from like a very specific, like you like very specific update here where the like everything is diagonal and equal. Right? And so how do we pick Q and R, like the noise for the measurement model? So often they're like either hand designed or they're bit. So you can like, let's say you got a bunch of Z's, you got a bunch of X's that you like knew. So like for instance, you like place the car somewhere that you know, and you like measure, you got a bunch of measurements, right? What you can do then is try to solve a linear regression problem. And the linear regression like coefficient will give you this. And then you look at the variance in like the residuals, and that kind of gives you the R. Right? So things like that. So often you'll fit the parameters like the filtering algorithm assumes that you know A, B, Q, C, and R, right? But you often like fit those either from data or from like knowledge of your system or something like that. Right?
So this part, this part, is your assumption of like all the sensors, or because I'm wondering like what if you have like one bad sensor and the rest are good?
Yeah, so like I guess what you'd have is then if you think of your R as like covariance matrix like that, right? Like you'd have like this element being really large and like these ones being small. Yeah. Cool. Any other questions? This kind of makes sense, Kalman filtering. Okay, so the nice part about Kalman filtering is that it's pretty efficient, right? So you can show that its complexity is big O of k2 to the or k to the 2.376 plus n squared. The way you get this is that this is basically the complexity of matrix inversion, right? And so you have to invert this matrix, right? And so like there's just, you can Wikipedia this. There's matrix inversion. Matrix inversion, like the generally efficient algorithms are that complexity, and then you have matrix multiply, which is this guy, right? So you have matrix multiply, and you have matrix inversion. If you don't assume things are sparse, then you have n squared for matrix multiplication, and this for matrix inversion. Right? So it's generally quite efficient. And you can show that it's optimal for linear Gaussian systems. This is like the best you can do. But most things in the world are nonlinear. Barely anything is linear, barely anything is Gaussian. And so what we'll study next is how to go beyond that. Yeah. It's useful in lots of different robotic systems, but let's go to the next part, which is EKFs, or extended Kalman filter. So the idea behind EKFs is, can I reuse a lot of the Kalman filter math for nonlinear systems, right? So when I think about a nonlinear system, let's imagine that I had a system where xt plus 1 is no longer axt plus but, right? It's some g of xt in ut plus epsilon t. So let's assume the system is nonlinear but Gaussian, right? And so the noise is still Gaussian, but the system is nonlinear, which means it's a nonlinear relationship between x, u, and the next x, right? And your measurement is nonlinear. It's like a nonlinear relationship between x and z through this function h, right? So it could be a neural net. It could be some complex polynomial. It could be, you know, a bunch of sines and cosines. It could be just like a complex function approximate. It could be a piecewise function. Okay? So we're going to assume that it's nonlinear. And this is true in many systems like robot arms and lots of cars, and like even the Musher car is not linear. And so the assumption we're going to make in EKFs is that you have a nonlinear system, but noise is still Gaussian. Okay. So it's useful in all of these cases, but how do we deal with nonlinearity? What's the magic sauce? So from all your calculus classes, like if I have a nonlinear system, but I only know how to deal with linear things, like, is there any magic sauce we can use? That's it. Right. This is Taylor. And Taylor series is the answer to everything. So all we're going to do is we're just going to use a Taylor series. That's all the EKF is. It's very underwhelming. Sorry, Violet. But we're just going to use the Taylor series. So just as a recap, a Taylor series is saying that if you have a function f, you can expand it as an infinite series around some point A by saying f of x is f evaluated at A plus a linear function, x minus A, times the gradient, plus a quadratic function times the second derivative, plus whatever, right? So in some sense, a first order Taylor approximation would be just the first two terms, right? And so it's not f of x, but it's an approximation to f of x, which is linear to x, right? So if you just take a function f of x, you break it up as a sum of these terms, and you just like pretend these terms are negligible, right? Then you can kind of treat this as a linear system, right? It's a linear system where the coefficients of your linear thing are determined by the gradient of your function, right? And so that's the like trick to most of robotics, really, is to make things somehow linear, right? So you drop higher order terms, you're pretending that your system is linear, right? So graphically, you can kind of think of your nonlinear system, right? And you can think of a Taylor approximation as like adding like different order polynomials. So like you have a constant, then you have like a first order thing, then you have like a second order thing, then you have a third order thing, and you kind of like add all of them together in order to get your really complicated function. But an approximation could be just to use the first order thing, right? Which kind of looks like this. So essentially this approximation graphically looks something like this, right? Now, what's the challenge? Like, can we use, like, can I just magically use this everywhere? Or are there some conditions where this holds?
I guess you have to go too far away.
Right. Exactly. So if your function is nonlinear, you can see that like it holds in some like tiny little neighborhood here, but like the further you go from your approximation, the less likely your linear approximation is to be, or from a point of approximation, the less likely it is to be good, right? So if you ever have like a function, you kind of want your Taylor approximation to hold in some neighborhood. And then after that, you have to like reapproximate. Okay? So you can approximate it here. Next time you move here, you can reapproximate it here. Next time you move here, you can reapproximate it here. Right? So you're going to use the Taylor approximation, and you're going to keep reapproximating things to be in the neighborhood. Right? Okay, so the key idea behind this EKF, or extended Kalman filter, is just to like linearize the dynamics and linearize the motion model, or the measurement model, which are nonlinear, right? So it's saying that just linearize those things around your current mean belief, right? So you have your current belief, let's say it's a Gaussian with mu t 0 to t, sigma t 0 to t. You're just going to like choose this point because you're like in that neighborhood, it's a Gaussian, right? And you're going to like linearize your motion model around this mu, right? And so the first thing you're going to say is let's think about the dynamics model. Okay, so the dynamics model says xt plus 1 is g of xt ut plus epsilon t. You want to write this as some xt plus 1 equal to axt plus but plus epsilon t, right? That's what you want to get, because I know how to Kalman that. I know how to deal with this guy. Now I need to go from there to there, right? And so the trick is you're just going to approximate it as a first order Taylor approximation. And so it's a little more involved when you have multivariate functions, right? So think of this as like, let's say this was x was of dimension, let's say m by 1. Let's say u was of dimension n by 1, and xt plus 1 is of dimension m by 1, right? Just vectors. What we're going to do is we're going to take the Taylor approximation around mu, which is the current mean. Right? So you're going to take the first term. If you remember the Taylor approximation, f of x is equal to f of a plus f prime a times x minus a. Right? That's what the Taylor approximation is. So we're going to stick that in here. So we're going to have like the first term. We're going to linearize. In our case, a is equal to mu t. So we're going to linearize around mu t. The first term is g of mu t, and this is ut, current action, right? And you're then going to take the gradient of this guy with respect to state, right? So you're going to say like, what is the gradient of the dynamics function with respect to state? dg xt ut with respect to xt evaluated at mu t, right? And so this is g is a m by 1 function. Xt is an m by 1 function. So this is going to be a matrix. This is often called the Jacobian, but it's going to be an m by m matrix, right? And in this example, we don't actually linearize with respect to actions, but you could, right? So in many cases, like I'm not going to work through the math here, but you can get away without linearizing about actions, but you could also have dg xt ut with respect to dut, right? But you don't have to, and you can kind of derive the equations without it. But kind of think of this as like you're taking your G and you're doing a first order Taylor approximation. Just remember that this is an m by m matrix, kind of like your A, right? So if you ever want to use Kalman filter math with a nonlinear system, you just do a first order Taylor approximation and treat it like a linear system. And you just have to redo this approximation often. Right? So you can do this, and this is going to give you something that looks like this. Looks a lot like the Kalman filter. It's linear in X. You can also do the same thing around your belief. So if you have your H, you can again linearize it around your belief bar. You can say that it becomes like a linear function in terms of xt. Right? So you can say that it's a linear function in terms of xt, and you just have some constants. Okay, so the only thing I really want to convey here, you don't have to like really get into the weeds here, is like take a nonlinear system, approximate it as a linear system with a Taylor approximation, run the Kalman filter. That's it. Okay, so so the way that you do it is you start by linearizing your dynamics, then you perform a dynamics update, right? And then you linearize your measurement around your updated belief, and then you perform a measurement update, and then you repeat, right? So you start, you linearize, then you perform the Kalman filter update, like A mu plus B, A sigma, A transpose plus Q. And then you linearize your measurement model and you perform the measurement update, you repeat. Right? And the reason you have to repeat all the way back here is that you have to relinearize you have to keep relinearizing your model because it's not always applicable. It's an approximation. So this is often called like iterative linearization. You're always like relinearizing your system around your latest point, latest neighborhood. Yeah.
It's a practice that are you also storing like the previous linearizations at like prior states?
You don't really have to, right? Because you're just like all of that is stored in your current belief. And so you just like relinearize around your current belief. You don't have to keep everything up. Good question. Okay, so the original Kalman filter algorithm was this, right? What the new Kalman filter algorithm is going to be is that you linearize your dynamics to start. You update belief to belief bar, just using the Kalman filter update. But just remember, you're going to like update G with capital G or update A with capital G. Yeah. Okay.
Does it get tracked back in matter correction?
Yeah, it gets tracked back in because you're doing like the measurement update again. So it's not, what it doesn't do really well with is functions that are extremely nonlinear. So it like works well when functions are kind of linear. And the approximation is good. Otherwise, you have to like take really tiny steps for it to make sense. But as long as that is reasonable, it like this step corrects back for the drift. Yeah, good question. So you perform the dynamics update. The only difference is that instead of A, now you have this like linearized function G that is changing from step to step to step. So G is estimated every single time. So this is G, this guy over here, right? And then once you updated your dynamic step, you get an updated belief bar. You relinearize your measurement around that updated belief bar. And then you perform the measurement update. Everything is the same, except your like your C function is replaced with like an H function, which is your like linearization. And then you do it, right? So that's all that an EKF really does. Make sense? Linearize, Kalman, linearize, Kalman, linearize. That's it. Okay, so why might we still want to use particle filters? Okay, so we talked about Kalman, it's simple. And it's like you could make it nonlinear, but why would we still care about particle filters?
I guess like one instance, if the uncertainty isn't like a Gaussian, like let's say you have two paths, then like you're gonna go.
Yep. So like you can go this way, this way. It's like a bimodal distribution, not a Gaussian, right? In those cases, particle filters make no assumptions about Gaussianity, but Gaussianness. But EKFs and Kalman filters do. What are other reasons? The other reason is if your linear approximation is pretty bad, right? So if it's like a pretty non-linear function, you're trying to move pretty fast. If your linear approximation is bad, this won't be great, right? And so non-linear functions, non-Gaussian functions, things that look nasty like this, particle filters tend to work well, right? But what's the con of using a particle filter? It's lossy. It's lossy and it's approximate. And you have all these like you lose particles in random spaces, and you have to do all of these hacks. And as you go to higher dimensional spaces, the number of particles you have to have like blow up. And that makes like, in some sense, Kalman filters are nice and tractable. Particle filters are like more general, but like computationally much harder to do. And so, yeah. Okay. So what have we learned? We've talked about Bayesian filtering. Bayesian filtering is combination of a prediction step and a correction step. That's the one for a discrete system. But we started, actually, I did this backwards so you guys could do your homework. But really what you should start with is the Kalman filter. And then you should go to the extended Kalman filter. And then, so this linear Gaussian, EKF is non-linear Gaussian, and then particle filters are non-linear, not Gaussian. Okay. So this is like probably the easiest, most general one to use. I'd recommend using it where you can, but Kalman's cool. You should know about it. Some history on Kalman, if you have like a second. It actually came out of like an Air Force program. Where there were Air Force program and the NASA program where they were trying to like send things to space and like track satellites. Like tracking. And it's used all over. It's used in chemical plants now. It's used in robots. It's used in all sorts of processes. Yeah, you can watch that later. But yeah, I think that's all we have time for today. We'll do discussion on Friday. And yeah, yeah. Thanks. And then you're in touch with your new team. And Tong should send you an email, but I think you know what to do. Hey, what's up? Do you have to sign something?
No, I just want to let you know, I'm a practice player for the basketball team,
Oh,
and so I
cool.
have to travel for the games this weekend at
Okay.
Ohio State and Penn State, so I won't be at the lectures
Okay.
Friday through Wednesday, but I'm pretty sure I can zoom in.
Well, I'm not here on Wednesday.
But yeah, this is just the form, just so you have it.
Okay, do I have to sign it?
No, it's
Okay.
just for your notice.
Excellent. Good luck.
Okay, cool, yeah.
Also, that's our number.